Okay, well, welcome back to week 2, another snowy day and another video instead of class. Um, so the material for this week is talking about the task-specific strength components. And so basically, as an overview, what we'll be looking at is characteristics of the movement that have some biomechanical implications for how we are going to, sorry, I stumbled on that word, implications for how we're going to consider the movement, train the movement, and help to get our athletes better in the movement. So the first concept we come to is the basic difference between velocity, power, and force generation. Now, we've looked at this in previous courses. We looked at this in, for example, strength conditioning and exercise physiology, and even in kinesiology. So I'm just going to go through this as a real quick review. What could be new to you, however, is some of the details, like this way of noting the muscle performance. So PM for power performance of the muscle, VM for velocity performance of the muscle, and force or FM. So these are abbreviations that get to the more technical side. As you've noticed, this book is kind of introducing you to that technical biomechanical understanding of strength conditioning and force development and resistance training. So anyway, that's just a new way to say the same thing we've already looked at in previous classes. Do go ahead and create definitions here, including, don't forget that power is a formula in a physics formula, so make sure you put that in there. So the next new thing that we might want to talk about or just review is the idea that of the force velocity curve. And so here is a basic force velocity curve. We're looking at different loads lifted at different kilogram weights, and then the velocity at which it can be moved. This, in this case, is measured in radians per second. So it's movement in an arc around a joint. But you can see it shows the same thing we've looked at before, that high velocity objects are going to need to be lighter objects, and heavier objects will be moved with lower velocity. Over here on the right-hand side, we see a force velocity curve that includes both concentric on the right side and eccentric motion on the left side, because velocity is on the x-axis. And in the middle is isometric, no motion. So this is moving backwards, eccentric motion, and contractions that move forwards, concentric contractions. And as you can see, we are in fact stronger eccentrically than we are concentrically. That is to say, and you know this from experience, you can lower a weight. You are strong enough to lower a weight that you cannot lift. You have this much force generation capacity, you can lower that weight safely, but you cannot lift it. You cannot move it concentrically. And so I love this graph because it definitely shows that very, very clearly. This part of the graph is the same kind of graph you would see over here. This is just showing you the concentric, and you can see the same curve pattern. What happens if you go up here? So the highest force you could possibly generate for an individual is a very fast eccentric movement. However, we don't really train at this velocity because the risk of injury is immense. And so really, in terms of training, let me get a drawing tool here. In terms of training, even if you're doing eccentric loading, you're going to, let me get rid of the fill. You're going to train, in this area, somewhere in there. So, below your maximum. So we'd never really push eccentric training. This would be very severe eccentric training. We would never push eccentric training out here. The risk of injuries is just too high. And there's at that point, there's really no benefit, just risk. Okay, get rid of that. Let's move on. Now, the new word for you today is maximum maximorum performance. This idea is essentially what are the movement characteristics that produce peak velocity, peak power, or peak force. This graph has two y-axes. The first one is velocity, so you have force velocity curve, and you can see that that is this curve here. And it's showing you exactly what we've seen before, that the faster you move, the lower the force, and the higher the force, the slower you move. The second graph axis is power. And so this is a force power curve. And that is this dotted line here. And it is showing you that peak power occurs in the middle of the force velocity curve. So the most powerful movements are neither very fast nor very heavy. They're in the middle. Now, this is a generalization. Each joint is going to have its own power curve. And if you get to multi-joint movements like a clean or a jump, the power curve for each movement will look a little different. But the peak power, the maximum maximorum power, is always going to be a little bit higher, or somewhere in the middle, higher than the peak force and lower than the peak velocity. It's going to be in the middle, somewhere in the middle. So this power curve may look a little different depending on the movement, the joint, but it will always have its peak somewhere in the middle. All right, moving on. So the next topic we have is parametric force velocity relationships and non-parametric force velocity relationships. And I went ahead and threw in the definitions for you here because this is definitely new and this is a little complicated. So the first example of parametric, this means that there's a relationship. There is a relationship. There's a clear relationship between, in this case, let me correct my notes here, throwing baseballs of various weights with the velocity with which you are able to throw it. For example, if we have a pitcher and he has a standard baseball, he will throw that baseball, let's say 90 miles an hour. If we take that baseball and replace it with a baseball that is, a 1/4 ounce lighter, we actually do expect him to throw that faster. He has less resistance, and so it should be able to be thrown faster. And if, on the other hand, we handed that baseball pitcher a 4 kilogram or roughly 9-10 pound shot put, would not expect it to reach 90 miles an hour. And so parametric means there's a relationship that as the weight goes up, the velocity of the throw will go down. Now, this is not just applied to throwing. This could be your movements as well. And we're going to come back to this because most of the weight room activities have parametric force velocity relationships. A non-parametric force velocity relationship is where there's a positive relationship instead of an inverse relationship. For example, stronger swimmers exert more force on the water and move faster. Now, this has to do with the fact that the fluid forces act quite differently than, like a weight in the weight room. The harder you push on water, the harder it pushes back. This is why, water is so devastating. If you fell from, 40 feet up above water, it's going to hurt like hell or injure you when you hit the water, because the harder, the more force you move into water, the more force it pushes back. It's not a normal parametric relationship. So typically non-parametric force velocity relationships are going to be associated with some sort of non-normal resistance form. In this case, water is a great example. Okay, so in this example below, or in this table below, what you're going to do is fill in some example sports or sport activities that meet the characteristics given. All right. The Next one we are going to, next topic we'll move on to is looking at the textbook and its use of some terms that you're pretty familiar with, only they, again here, change the terms to be more specific to the biomechanical perspective. And this is going to come up with the idea that we would have meometric, plyometric, and isometric movements. And so let's take a look at those in just a little in a little more detail. If you're looking for this in the textbook, it is on page 19. Now, meometric just simply means a regular concentric contraction. A plyometric contraction is associated with the stress shortening cycle. But specifically here, we're looking at eccentric. And so they're using the word plyometric to contrast the meometric of concentric. So plyometric here is being used to refer to the eccentric action. And then isometric is exactly what it is. It's not different. It means no motion. So it's the development of force with no change in muscle length. And so here, you're just going to apply these terms with different types of forces. I guess the next topic was intrinsic forces versus extrinsic forces. And the book goes into and talks about how some of the forces acting on the body are outside of the body, some of the forces acting are inside of the body. I believe you can find this on page 20. Yeah, so it's on counter 1920. Take a look and you know, fill in here some examples of these types of forces to demonstrate your knowledge of them. The next topic is where it actually gets interesting. This chapter has tons of great information, and I feel it starts right here. So this topic is the idea of rate of force development. We briefly touched on this in 260, if you've already had 260, and that is that if we look at the force on the y-axis and time in seconds on the x-axis, that from no contraction to maximal force development, it's going to take time. And then you can see here, the 0.5 FM is how long it takes. That's the T, 0.5. This is how long it takes to get to half of your maximal force. So rate of force development is essentially looking at the slope of this line. And rate of force development is far more important in most sports than actual maximal force is, because as you will see, actually before I move on, let me draw some here. If somebody had a rate of force development, let me create a squiggles. If somebody's rate of force development was like this, we see that they are not only weak, their maximal force is low, but they develop that force quite slowly. And so, you know, halfway between here and here is here. So let's say this is the halfway part, that it took them longer to get to their halfway part. That's two physiological variables for this athlete that demonstrate they're not going to be powerful. Not only do they have low maximal force, they take longer to get halfway. That's how we would look at rate of force development and figure out if an athlete is, you know, going to be a good power producing athlete. And then, whoops, that's not what I want. I want to change my pen color. I want this, and I guess I want this. And then let's take a look at another athlete doing the same thing, and let's build ourselves like our ideal athlete. Our athlete is who is going to be powerful, who is going to create tons of force with really quick development. And so I'm going to draw, I guess I'm not going to draw, come on, draw. Here's an athlete, and they're get up to their maximal force, even if it's the same as this maximal force, they get up there faster. And so in halfway, in this person is going to end up being over here closer to this side. I know it's really badly drawn, but that means this athlete develops force faster and will be a more powerful athlete. Okay, let's move on. Now, this is some application questions, looking at application of this information. There's also some terms here that relate also to this idea of rate of force development, and also what we call the explosive strength deficit. And that is how much force, we can measure how much your maximal force generating capacity is, using maybe a maximal lift or a maximal isometric lift. But when you move explosively, you're not able to express that full amount of force. And so the explosive strength deficit is how far away from your maximal force you are when doing an explosive movement. And this again is another measurement, another way to think about force and power that helps us understand an athlete's movements better. So there's some questions in here, and then there are some definitions that I want you to fill in. Resistance types. So resistance types, we looked at this quite a bit, in 260, but this book is really reinforcing a few forms of resistance training, resistance types that are going to be kind of standard ones. So we have elastic resistance. Go ahead and read the book's section on this and give a little summary. Inertial resistance, that is where you have the inertial wheel. It's actually growing in popularity as a training tool, and it's especially good for training eccentrically. And so I want you to go ahead and watch the video I've provided here on that. And let me. The next one is looking at regular weight resistance. This is using anything that's heavy and controlled by gravity, pulling down on it. The compound resistance and accommodating resistance. This would be compound resistance is when you combined band and chain plus weight, and accommodating resistance is when best example is chain, where it gets easier at some point in the exercise, especially to match our the way that our joint or our movement is, such that let's say at the bottom of a squat is the hardest part of the squat, and so it gets lighter at the bottom of the squat. That's exactly what chains on a bar would do. Now, the most common way to use chains and bands is to use a bar with both a band or chain as well as some weight on it. It's very unusual that an athlete would lift band exercises with 100% band. That's not really a common way to train the basic barbell lifts. We think about bands being used, for rehab, where you would just use a band as your only source of resistance. But in sports training, we usually use compound training, band plus weight on a bar. So anyway, there's two videos in here. The first one is about the inertial trainer, and it's a very nice video that shows you lots of example exercises using the inertial trainer. The other one is a video comparing bands to chains, the relative benefits of one versus the other. But also in that video, they talk about combining band and chain with weights, so a compound resistance. What I'd like you to do in this section is just define these for the videos, give a quick summary, one or two things that you learned from watching that video. Okay, now we get back to the concept of rate of force development and how quickly we can move an object. And this is, again, playing off of what we saw back here, because I gave you the example here of sprinting. You see, when you're sprinting, your foot is only on the ground for a very, very short amount of time, 0.08 seconds to 0.12 seconds. And the better the sprinter you are, the less time your foot's on the ground. The better the sprinter you are, the more time you are not touching the ground. So when you are touching the ground, you need to generate as much force as possible in a very short amount of time. Now notice here, 0.08 to 0.1. When sprinting, you are not even getting up to an average for most people. You're not even getting to your 50% of your maximum force. You're moving so fast, your foot is only on the ground long enough to go from no force to this much force. And so that is the challenge, is to get athletes to have higher rates of force development so that they can move faster, so they can push into the ground faster, so that they can jump higher, etc. Same thing happens with jumping. If you are really good at jumping, you get off the ground faster, but that is a hindrance because the faster you move, the less force you can develop, unless we train rate of force development. And so here we go back to our concepts of rate of force development, and we looked at all of these, and it goes into, and I want you to explain the reactivity coefficient, the force gradient or S gradient, the A gradient, and velocity. These are additional forms of calculations that can be used to describe rate of force development or its related concepts. And what I just want you to do is define them here, and then I want you to think about how one or more of these terms might be a better way to think about the needs of an athlete. And I gave you two examples here of a sprinter coming out of starting blocks and a basketball player jumping and rebounding. So think about how these different modes of discussing or thinking about rate of force development might have greater or lesser implications to different sports. I will tell you, they all have some connection, but see if there's one or two of them that match best in your mind. All right, so the next one is we're going back to those force velocity curves. And so just thinking about that again, the book, whoops, on the list. So I just would like you to draw a force velocity curve for any specific sports movement. That's all you got to do in this space. Be specific. It's going to look a lot like the ones I had it for you at the beginning of the presentation here. Next concept is a quick release. This is a training technique that allows for greater force development because essentially what we're doing is causing an isometric contraction and then releasing the athlete to move. And so they're able to develop greater force because we have this, we're basically holding them back. And then when we release, their body will move with greater velocity than they could without this technique. Quick release techniques are used. This is the term is also used by various sports coaches who are like hockey. You get the puck and I want it off your stick really quickly. That is not what we mean by this. In this, it's going to be an isometric contraction when then whatever stopping you from moving is suddenly removed, and you will move faster than you could if you had not put the isometric contraction first. The video here is an example of this using a sprinting harness. You put the harness on and you're basically holding the athlete back, you're holding them back, you're giving them resistance so they cannot move, and then you suddenly pull the string and they release and they can speed off, accelerating faster than they are used to. Now, the benefits of quick release training is to increase velocity, increase speed, and basically train the brain to move faster. So we talked about last week transferability. This is a technique that's used in an effort to train transferability to acceleration power and rate of force development in different movements. It's a technique. It's not the end all be all, but I want you to think about how this might be applied to a sport that you're interested in. Let me fix this. Spelling error. Let's move on. Then we get to the stretch shortening cycle. And of course, the stretch shortening cycle has to do with rate of force development as well, because a good stretch shortening cycle is going to have a very short time, and it's going to develop as much power as possible. the first thing I want you to do is remember what the NSCA called the 3 parts of the stretch shortening cycle. You can look that up if you need to. But basically just recall, starting place, what the stretch shortening cycle is. Next one is I put in here for you the 3 things that affect force development in the stretch shortening cycle. So the first one is the neural mechanics, which includes the myostatic reflex. That's the muscle spindle fibers. The book had a nice, like, page and a half description of how the the muscle spindle fibers sense a sudden stretch, and then they cause a reflex to occur that will cause the muscle to contract. And so it's a reflexive contraction. So one component of a force development in a stretch shortening cycle is reflexive, the stretch reflex. The next one is the series elastic component, or the elastic potential energy. The book talks about how the muscle and the tendon can both store elastic energy. So basically, when the muscle and the tendon are stretched like a rubber band, they want to go back to their original shape. Please note in the textbook, and I'm telling you now, that in highly trained athletes, the stretch comes primarily from the tendon, not the muscle, because their muscles are contracting so completely that really the tendon is the only elastic component or the major elastic component. In less trained people, the muscle will have a bigger role in the elastic component of the stretch shortening cycle. And you don't really have to train that, because if you train the stretch shortening cycle and you train your athletes to be stronger, then it's just going to happen on its own. Also, you have your usual muscle actions where your brain is sending signals to perform the motion. So we have the contraction being caused by the myostatic reflex, added to the neural impulses being sent from the brain. And so these 3 things are going to result in force development and rate of force development that might be higher than what it was if we did not do the stretch shortening cycle. That is why you are able to jump higher if you step into the jump as opposed to doing it from a static position. That is why you are able to rebound higher than you are able to jump from a static position. That is why you are able to sprint and take a larger step than if you were standing still and I just asked you to jump 1 step. And so that's the stretch shortening cycle. I am at this point assuming that you have studied the stretch shortening cycle before. If you have not, I do recommend you maybe find a YouTube video just to cover this in a cursory way before you look at the specifics, because this book goes into much more detail and might be over your head if you didn't have a pre-existing knowledge, which you should have if you took 260. All right, the next piece of information, I pulled this out of the book. This is figure 219, and this is a research study that is looking at how do we train the stretch shortening cycle. So in this study, which is from 1985, which is, I always tell you guys that sometimes the best research studies are kind of old because they did really good stuff. And when the question was answered, no one's really redone it any better than this. But this was there are a few others. This was one of the early studies looking at power development in athletes from 1985. And the 2 authors, Hakkinen and Comey, who are quite famous muscle and sports performance researchers, they took 2 groups of people, and in both cases, what they did is before, which is the circles, you can see before circles, they had the athletes do drop jumps. This is where you stand on a platform. The platform heights are on the x-axis. So a 20 centimeters platform, a 40 centimeter platform, a 60 centimeter, 80, and a 1 meter platform. And then they would just drop off, so slip off the edge of the platform. And when they landed on the ground, try to rebound and jump as high as possible. This is a form of plyometric training you've probably seen before, again, called drop jumps. And you can see that at the beginning of the study, group A, performed like this. Basically, and you can see the stretch shortening cycle. When they dropped from slightly higher heights, they were able to jump a little bit higher. That's because they were storing more elastic energy, and then they were, returning that energy into a higher jump. Great. But if you drop from a height that is too high, and this happens a lot when overzealous coaches give athletes activities to do that are too difficult. If you drop from too high of a height and rebound, and you're not strong enough to do this, so essentially what happened here is these athletes were not strong enough to rebound. They basically landed too heavy and just jumped, and it was, essentially the same as if it was only 20 centimeters. So this was too high for them. So what I would know from this initial pre-curve is that I should train my athletes in this range, and that this was too high of a box for them. Now, the other group, we're still on pre, the other group did the exact same thing, and you can see they had a very, very similar pattern. In this group also, the 1 meter box is just too high for this group of athletes who are not strong enough to handle it. Now, that's our first takeaway, is that stretch shortening cycles are going to improve performance, but only if the forces that are the body is being asked to generate are possible. And in both of these groups, 100 centimeters, 1 meter boxes were too high. Now, after the study, let me tell you what they did differently. Group A was given resistance training. They were working for heavy resistance training, building strength. And so they were doing basically all the training based on let's get stronger, let's get stronger. And what you see is that their performance at the end in the square boxes, it does go up a little bit, especially at the lower box heights. However, it's not impressive. This is not an impressive improvement in the peak power range. There was really no improvement in peak power, only in these sub-peak powers. And the other thing to notice is that now that they were stronger, they were able to handle that 1 meter box better. So that's good. But this is unimpressive transfer of training. These heavy resistance training did not improve their stretch shortening cycles and their power and their rate of force development in the ways that we would really like to see, unlike Group B. Group B did explosive power training. So this is going to be moving the bar, lighter bars, much quicker, and using lifts that are designed for power, like cleans and things like that. And you can see that there's a huge increase in the power when the jump heights for these athletes who are doing these drop jumps. However, you can see also clearly that they were still performing subpar when it came to this 1 meter box, whereas this group flattened out their curve. This group was not able to flatten out their curve. And so, a takeaway from this, the thing I would say about this research study is that it clearly shows you have to train power to increase power. You have to train power to improve your stretch shortening cycle. You have to train power in order to get a higher vertical jump, or in this case, a stretch shortening cycle, a rebounding jump. However, there is still the necessity to have adequate strength. And that is why periodization is the best form of training for athletes, where at some point in the year, I can get all my athletes really strong. But at the end of that training, they still have to do power training, as the season gets closer, in order to get usable strength, or the kind of strength that's going to show up in performance. And so it's not saying you should not train your athletes with strength training. It is saying that you must not only train your athletes by strength training. We need periodization. Now, I want to tell you, and I like so important. I'll be looking for this in your assignments to see if you've heard this carefully enough. One of the things that I have definitely seen in especially youth coaches who are good but not great is that they'll take their young athletes and they'll do tons and tons of explosive power training, and the athletes will get very good very quickly. And that's why these coaches have like the reputation for being great coaches. They do this type of training, they get their athletes good really, really quickly, and then the athletes plateau and never get much better. It's so predictable. It's so predictable. Because then what they should do is then cycle in a periodized plan and go back and get stronger, then get more powerful, and then go back and get stronger, and then go back and get more powerful. But what happens with lesser trained coaches is that they do this type of training and they see huge benefits, and then they just stick with that and forget that they, or never knew that they are going to cause their athletes to plateau. They get quick, great results, make some great coaches, but they don't know how to continually develop the athlete. And so watch out for that and don't be that guy. All right. The last concept we have in the textbook, this chapter that I want to talk about, is the idea of how joint angle affects the force generation capacity. And so basically there's, oh my gosh, there's so many pages on this. And it gets really complex and detailed. I don't know that we need to spend that much time on it, but it is an important thing to note that each joint, each joint has a different force curve. Each joint is going to have different force generation capacities at each joint angle. And so over here in the side one is 3 kind of theoretical examples. So here's a joint where as the joint angle increases, the force generation increases. So you start out with, maybe if this joint is at a small angle, you're very weak. And then as the joint extends or flexes, you just get stronger and stronger and stronger. Or the opposite, whereby you get stronger, you're stronger at a small joint angle, and then it gets less and less and less. This is one of the more common ones. Really, again, each joint is different, each motion is different, but this is a common one. We talked about this version in kinesiology. We only talked about this version in kinesiology, whereby you're strongest in the middle of the joint angle. So what is the cause of these patterns? Muscles. Some, different joints have different numbers of muscles around them. They have different sizes of muscles around them. They have different shapes of muscles around them. And so each joint is anatomically just different. The next 2 graphs are 2 real examples, not hypothetical. These are real examples. So this is elbow flexion, and you can see it has the classic pattern I showed you in kinesiology, whereby force generation is the greatest around 90 degrees, right at 90 degrees by this graph. And then over here, you can see shoulder flexion, which is strongest when your arms are down by your sides, and you get weaker and weaker and weaker the further your arm comes up and away from the body. And this is not surprising given the way the muscle of the shoulder exists. You have more muscles able to contribute when the arms are down low, and you have less and less muscles able to contribute the higher up you go. You have all the kinesiology factors playing into this. Now, this just is a fact. This is anatomical fact. We can make an athlete stronger in a particular joint, but in the end, it's going to look very similar. So let me show you some examples. If I train an athlete and they do tons and tons of bicep curls, maybe I get an athlete who has greater force development, but it's still going to have more or less the same pattern. And if I train an athlete and they have, maybe I'll do some really intense training at a specific angle. So I'm going to train shoulder flexion, but I'm really going to highlight this area here. I'm going to train in that particular range of motion for, that's not what I wanted. I wanted fill. Let me make it gray. I'm going to train in that region. Maybe I will make it. Maybe I won't do this. Okay. No film. If I do this, if I train this athlete and we train that region of the curve specifically. So when we're doing exercises, I isolate this particular region of the curve. Okay, here's what might happen. I'm going to take that and I'm going to have more or less the same pattern. I might be just a wee bit stronger, and then I might create more of a gap in that region, and then I'll have go back to my regular pattern. And this is what we would call angle specific or specificity of joint angle training, where I'm creating the muscles that do exactly this portion of the motion. I'm getting them stronger. So this is about all you could do to change the shape of the curve, minus a catastrophic injury or something. It's still going to have more or less the same shape. We've just created a little more separation at one particular part. That is the best you can do to change the shape of the curve. That's it. And then this is all much, much more complicated when you get to a multi-joint movement. And so here is isometric pulls occurring at different heights. And so basically the bar is set and cannot move, and you pull as hard as you can and you measure the force. And then we set it just consistently a little higher until you get up here and you're trying to lift the bar while it's still over your head. And you can see that there's a pattern here that happens where you are going to be strongest here, which we would call maybe our second pull position or our shrug position. This would be exactly where we explode in the clean. That's exactly where the strength peak is. And then you get very, very, very weak up here. This is why, someone doing a snatch is not actually lifting the bar. They're actually pushing themselves under the bar here. They can't lift this bar. You cannot lift this bar. You cannot lift this bar. At this stage, you are far too weak to actually lift the bar if it's the right weight for this stage. So multi-joint movements have their own patterns because there are multiple joints combining together to create forces. So anyway, last question on here is just to try to summarize the application of this material. What I am asking you is, as a coach, what do you take away from all of this information about the movement, task-specific strength? How do you use this information to build better athletes? I did say one sentence. I won't hold you to that. You could have a few more sentences if you want, but try to really boil it down to the real takeaway message. All right, that is all for today. Hopefully I will see you next week in class. I'm really hoping on that. All right, talk to you soon.